Okay, for a numeric variable, something on a continuum, a numeric continuum, as you know, we use histograms to do the counts. We still can have frequency distributions, but with numeric variables there are many, many, many potential different values typically. And because there's so many values, we have to bin the values together, kind of group, in other words, group similar values together into what are called bins to kind of organize our data. Otherwise, we'll just end up with too many unique values. It's like if you had a bunch of people with their salaries like we have here, every salary is unique. It's a numerical variable and every salary is unique, so it's kind of a boring bar chart. We could do a bar chart of salary, but it'd just be a bunch of values all just a 1. So a frequency of 1. So what we do with histogram, we form bins and then we count the number of data values inside of each bin. So you should now already know, without even looking at the computer screen, how to do a histogram unless R. If you want a histogram, you call up the histogram function and start it with a capital H. And then give the variable name. So let's do the histogram of salary here. I'll run this one. Here's histogram salary is the function call. And now we get, again, descriptive statistics. We get, now because this is a numerical variable, we can actually count, we can calculate the mean, the standard deviation, the minimum, median, and maximum. We get an outlier analysis according to a box plot criteria. And we can see if there's any small or large outliers in the data that might potentially be of interest to look at. And we get the frequency distribution. In this case, we can see that the bin width is 10,000, and R came up with 10 bins. So that is the default bin width of 10,000. And here is our histogram again in blue. And we can see that the data is basically the most occurring intervals are between 40 and 50,000 and 50 and 60,000, and then kind of skewed here where we get a tail off to the right where just a much smaller number of people are making more money than the rest. So that's our histogram function. And we can also abbreviate it. HS is the abbreviation. Notice the abbreviations are always in lowercase. HS and salary, and if we want, we can specify a bin start and a bin width. So we can end up with customize our histogram. Usually, when you do histograms, you look at alternatives to the default bin width. The default bin width is picked by some algorithm that our system is using here to come up with the bin width. But there is no right answer to it. There is no one, this is the right bin width. So usually we want to kind of explore a little bit and maybe even not only change the bin width sometimes, but also change the starting bin as well. There's also a bin.end to keep, if you're looking at a bunch of different histograms and some of the histograms don't expand the full range of data, you can end it at the full range of data so that the histograms are more comparable with each other. At any rate, let's just run this histogram here. And now you can see the bin width is 12,000 instead of 10. And there's the histogram we get, which is a slightly different looking histogram than we had, the bin width of 10,000. So you'll almost always want to play with that bin width parameter to get a sense of the distribution. We can also do a smooth curve instead of a histogram. That's called a density function. So density, salary. And here's the smooth curve. We actually have two smooth curves. We have one where we assume normality, here, the blue one, and one we just look at the general density without making any assumption of the underlying distribution, which is kind of the pinkish brownish curve here. And I give you the overlap with the histogram in the background so you can kind of compare it to the histogram and also kind of the smoothed out versions of the histogram, assuming normality or not assuming normality. And you also get some statistics here with the density function, including whether the distribution is normal or not. And also you get something called a density bandwidth. And if you change that bandwidth with the BW parameter, you can make the density curve smoother or a little more rougher, if you will, a little rougher in terms of the smoothness parameter. So sometimes if you're going to be serious about your density function, you probably will explore different bandwidths as well, just like with the histogram, you explore different bin widths. So there's another function to look at the distribution of values for a single numeric variable, and that's called a line chart. Now the line chart only works when, or only is meaningful, it always works, but it don't for numerical data, but it's only meaningful when the data are ordered by some kind of criterion. Usually it's time, doesn't have to be, but usually it's time. So if you've got data collected in a time sequence, then in addition to looking at something like a histogram to see the distribution of the values, you also want to see how the values are distributed over, for example, time. And to do that, you run the line chart program, and line chart, or LC. You already knew the LC part, right? You should be able to guess that by now. And the line chart here then is basically the plot of the function data values from the first one, second one, third one, all the way to the last one here. And it also does a run analysis here, looking at the runs and looking to see whether there are individual runs in the data or not. And then there's also a box plot. And here's our box plot function. Here's a box plot of salary, along with all the box plot information here, such as whiskers and so forth, and hinges. And we have a scatter plot of salary. This is a one-dimensional scatter plot, so we get the same descriptive statistics as we did with the histogram. But we also get instead of bins, we just literally plot each individual point. The points are plotted with a translucent background, so you can see overlap between the points. If the 2 points are more or less taking up the same space, things will get darker, and outliers will be indicated with the red. So that's so-called a one-dimensional scatter plot. And we also just have the straight summary statistics again right here without looking at any graph at all. And also, in terms of the summary statistics, if I call up the summary statistics function, I get a lot more summary statistics than I get from the scatter plot histogram functions. I get kurtosis, skew, and quartiles as well. But if I just want to see what comes out with the other functions, I can call up SS brief, and a lot of my functions have a brief form. You can either put brief equals true as an option in the function call, or as an abbreviation, you just put period brief after the abbreviated function call name, SS brief. And this will give you the brief version, which is what you get with the histogram and the scatter plot functions. So that's, and just to show you something here, there's another advantage of less R beyond just the simplified function calls is that there's a lot of error checking going on there too, so you don't have to depend upon R errors messages, which are often very cryptic and also, to the uninitiated, undecipherable. So let me just, for example, show you what happens if I misspell the word salary here and call up a histogram of a variable that essentially does not exist. And when I do that here, histogram of the misspelling of salary, it will say error colon, and when you get this format, error colon and a bunch of dashes, that means that it's my less R function error. I trapped the error before the R system got it. And I try to explain in English what's going on here. You are attempting to analyze the variable misspelled salary in the data table called my data. Unfortunately, the variable salary does not exist in my data. And here are the variables that currently exist in my data table, and you can see there the misspelled salary. So I try to trap mistakes, so that when you can look to see what went wrong, and then figure out what went wrong, and then recover and redo the analysis. So that's counting the data values for a single variable, bar chart and pie chart for categorical variables, and histogram, density, scatter plot, box plot for numerical variables. That's our introduction then to frequency distributions for a single variable.